Swayam Prabha. Digital India. Educated India.
So now we are basically asking, so just to recap slightly as to what I said before lunch. So we are now at the case where the answer to the original question, does there exist a seeding that would allow W to win, that would allow V star to win, the answer to that question is no. Okay. So now the modified question is there a way to fix some matches that would enable V star to win, right? And we sort of agreed that if I am allowed to change log n being the number of players, okay, you can call it m, I guess, number of players, then log, if I am allowed to change the outcomes of log n number of matches, then there exists a way to ensure that V star wins. So now the question is, can I do in less than log n? Specifically, if I am given a value L is the number of arcs I am allowed to reverse, or rather the games that I am allowed to fix. For this given value of L, does there exist an SBA such that L arcs have been reversed and that, that the new graph, the new win-lose graph has an SBA rooted at V star. Okay? So that's the question we are asking. All right. So the input is the win-lose graph, and the input also comes with the value L, for instance, and so we are asking whether there exists a seeding that would enable the favorite player to win. Here also we assume that we have so you remember the affected set, that these are the players that are participating in those upset matches. Okay, so the same thing holds. Suppose, assume that we have this. So it turns out that this question can be, just to give the sort of ending away, right, like movie in a flashback. So it turns out we can answer this question in 2 to the power n poly n time. So look, first and foremost, I probably should say why this problem is hard. It should be easy for you to see, because if the original problem was hard, just finding a seeding without any reversal of arcs, that tells me for arbitrary value of L, which is the question that I am asking now, that if I am not allowed to bribe anybody, the question was hard. That was the content of the previous talk. So for an arbitrary value of L, the problem can only be more harder, right? Because it's a more general question. So the hardness prevails here for this question. So this is why we assume that, okay, the best we can do is an exponential time algorithm. This is a single exponential time algorithm. So you can see, so that if you are wondering why I have written it this way, 2 power n into polynomial in n, poly n should be subsumed by that thing. It is basically to emphasize as to that there is basically you have to sort of make 2 to the power n number of choices, and so this poly n, this is sort of a matter of, this is where the main work is done, and this is sort of some amount of bookkeeping and so on and so forth. Okay, so this is I just wanted to mention that, because if you are wondering why it's been written separately, it's because of this. And of course, this is the time complexity, and this is poly n is the amount of space taken. Okay, so okay, and another algorithm that we can give answers this question in 2 to the power ordered k log k poly n time. So this basically makes this is the same time complexity as our original problem, right? And why? And this is because basically we solve this problem by reducing it to the instance of our original problem, and then we use that algorithm. Okay, so this reduction from this problem to the problem where no bribery is allowed, that takes no more than this much amount of time, and then we invoke our that previous algorithm, and we know that is the time complexity. This is the time complexity for that algorithm, and therefore the whole problem can be solved in 2 power ordered k log k poly n. Okay. All right. So Before I start before I sort of go into the algorithm, I will first describe some properties, okay, some structural properties we will explore. Using those because those properties hold, okay, using those, we utilize those properties to design the algorithm. So if I just tell you the algorithm, it will make absolutely no sense. But once you know these properties, then it will make sense as to what we are doing, why we are doing. So obfuscation means basically when you're hiding something, you're trying to sort of prevent. So these are after all manipulation problems, right? Like somebody is manipulating, somebody is trying to do something underhanded thing. So you don't generally want outsiders to know about it. So you want to hide that as much as possible. So in that way, I'll be defining a couple of operations that we perform on the SBA. And they can be viewed as some kind of obfuscation operations. Like you're basically trying to hide the matches that you're trying to fix and so on. Okay, so the first operation would be called subtree cleanup, and the second one is called cyclic shift. So we say an operation is valid, okay. So an operation will take in an SBA, okay. It says if it is valid if it returns a subset. So in this case, we are assuming that not import. We have, so the win-loss graph D, correct? We have our favorite player V star. We have the number of arcs we can switch, the arcs we can reverse, number of arcs this, as well as a set of arcs, let's say R. So R is subset of the arcs in this win-loss graph D, okay? And the size of R is at most L. So this is the thing. Suppose we have this set R, okay. We are going to say that an operation is valid. So this operation works on B and R. So B is the SBA given to me, okay. And I have the subset R of vert edges whose direction has been switched. So if those vertices, if those edges appear in B, then they appear in the reversed form. Is that clear? So of course, every vertex incident on any edge in R will appear in B because B is a spanning tree, right? So every vertex has to appear. But there is no reason why every vertex sort of, this edge, so if an edge in R is present in B, you must read it as like it is present in its reverse form, okay? But R has been defined as a subset of edges in the original diagram of D. Okay, so you'll see why this sort of thing is sort of important, like as we go through it. So an operation is said to be valid if it returns some subset R prime. This is also a subset of edges, okay, which is of size at most L, and the new sub SBA B prime, okay, rooted at V star. This is that guy V star favorite, such that only the arcs in R prime are reversed. So in B, only the arcs in R were reversed, right? And after doing a valid operation, I will obtain another B prime, another SBA, in which the root remains the same. So in B also the root is the favorite, okay, same thing. And here also the root will remain the same, but the subset of arcs reversed may be different. So R prime can be different from R, okay, but the size of R prime cannot exceed L. Is this clear what valid operation means? So if you can sort of see ahead, what's going on is that we will take an SBA, okay, make some modifications to it, okay, and obtain another SBA which satisfies this property, okay. So what would that mean? What would that mean? So if I started out with an SBA which was rooted at V star, contains no more than L reversed arcs, that is a valid solution for my problem, right? That I am allowed to reverse L arcs and V star should be the SBA. Then I am saying that by doing these operations, I am creating another SBA. There also the root remains the same, the number of reverse arcs does not exceed L, but perhaps the arcs I do reverse is different. And why do I care about this? Because maybe the way I reverse arcs in R prime has a lot of structure to it, and knowing that structure can help me design the algorithm. Okay, so that's the idea. So basically, what we will do is start with an arbitrary SBA rooted at V star. Suppose such an SBA exists. By doing these valid operations, I can convert that one step at a time to another SBA, okay, where I have a very sort of a precise characterization of the set of arcs that has been reversed and other aspects of the tree. And that type of an SBA is the one that I will be looking for. Because if the original SBA existed, then this must also exist, and so on, if and only if. So answering the original question would sort of boil down to finding the SBA with all these structures. Okay, so that's the goal of these operations. So the subtree cleanup operation. Okay, so this is the topological order, or that rank order. So these edges, this one, okay, I'll just color them red. So I was going to draw these things by hand, then I realized I'm not doing a good job of drawing here. So I took the liberty of copying these diagrams from our paper. Okay, so these are red arcs, you can see, right? No. Okay, so all the missing arcs are the forward arcs, from left to right arcs. So these are the upset outcomes, right? Because a higher rank player C is being beaten by a lesser player V, right? So these are the upset arcs. So this is the topological ordering, and suppose this is the example, this is the SBA I have, okay? And this is the B prime I will. So the blue arcs are the one that represent the reversed arcs, okay? So between V and U, okay, if you see here, the order of the arc direction between V and U is U beats V, correct? That's what I said, because U appears before and there is no arc going back, so U beats V. But here, clearly we have switched the order, we have switched the direction, right? So similarly for blue, this one, okay, I don't know, this is as W, it should be star, let's just say V star, okay? Notational inconsistency, sorry. So if there is a confusion, please do ask, okay, don't get lost in all these notational inconsistencies. So from now V star to A, I see that, okay, between V star to A, again A beats V star, but here we have switched the order and V star is beating A. So these are the only, and rest you can check that all are fine. So here basically L is equal to 2, all right. So when is this operation used? It is used when V star has a child, okay, on whom the subtree contains a blue arc. In other words, when all the blue arcs, meaning the reversed arcs, are not incident on V star, only then do I perform this subtree cleanup operation, okay. Do you understand what I am saying? When you have a situation like this, that there exists a blue arc in this SBA, but it is not incident on V star. This blue arc involves V and U. So this is the time, this is the thing, this is the situation where I would sort of perform the subtree cleanup operation. This arc, as you can see, is fine. One of its endpoints is V star, the other one is A. This is fine. This arc is not the reason I am performing the subtree cleanup operation, okay. So how do we perform this operation? So I go down the tree and zero in on the subtree on which the blue arc is incident. So we always have the arc pointing downwards. So I look at the root of the subtree where the blue arc is pointing from the root to one of its children. So that would be this subtree, correct? Bad drawing, but okay, you get the picture. So I just look at the vertices in this subtree. So let's call it TV because it is incident, it is sort of on V. And I look at the subset of vertices that appear here. So that is the set V of TV, okay. Now I look at the induced subgraph in the win-loss graph on only these set of vertices, okay. So in this subgraph, in this induced subgraph, I do not have any reversed edges. This is where it's an original win-loss graph, okay. This means that induced subgraph. So from here, so I take this subtournament, I find any SBA in this, does not matter who the root is, and arbitrarily I sort of I create an SBA. Okay, this can be done like just do a depth first search sort of a thing, and you can do this. Doing so, I replace, so from here I find a T hat U, let's say. Okay, this is the SBA on sort of SBA in this D of, let's call it something V of TV. Okay, this is this thing. Instead of this, I pluck out this subtree and replace, oh, it's also using U here, so I did not see that. So instead of this subtree, I replace it with this subtree. Okay, you will see that the set of vertices appearing in this subtree and this subtree are identical. That is by construction, because I only looked, the SBA that I found was from this SBA in this subgraph, which only consists of vertices from this subtree. So I basically possibly this T hat of U, this is this thing, I replace this. Okay, now I do one other check. Now U has become the root of this subtree, correct? Now I go back and check, is V star U a part is an arc in the win-loss graph? If it is actually part of the win-loss, if it is an arc in the win-loss graph, okay, meaning this V star actually beats U, that's the question I am asking, right? So in this particular, if that is the case, then I do nothing, I just add an edge between V star and U, because this edge already exists in the graph, right, in the graph D. However, for this specific example, we see that, well, V star and U actually beats V star, right, in this graph. So then, if I wanted to make U a child of V star, I need to flip this edge. So this is why I change R prime, R. Remember, I had a set R consisting of these two blue edges, right? Now I define R prime. Can you guess what should be my R prime? R prime should tell me the set of reversed arcs in this SBA. This should give you some hint. No? What did I do here? What all reverse arcs what did I change here? I said I just basically moved, see, this was a blue arc because we needed to beat U, right? I created I replaced this subtree with another subtree that already exists in my original win-lose graph. So what that means is, I am not allowing any blue arc to appear in this subtree. Do you agree? I basically got rid of this blue arc, because I don't have to, I just found some vertex U to become the root of this thing, and I replaced it with this. So now, how can I change my, what should be the new blue set in this SBA? So is it not the case that, look at the blue edges in this subtree. They no longer exist, right? So then remove all them. So take from R, remove all the blue edges that existed in this subtree. So that is this set, right? R minus ATV will tell you that all the blue edges that exist outside of this. And I take union of U of V star if this is the edge that so basically if in the original graph D, as such as in this example, if U is beating V star, then this is the edge. Now this is the edge that I will now flip. So I add this to my R prime set. At the very least, so what happened here? So basically, I made this switch because there was a blue edge here, right? By removing this blue edge and replacing with a blue free portion here and adding maybe at most one blue edge here, I have reduced, what I have done is, maybe if there was exactly one blue edge here, then here also I have the same number of blue edges in this B prime. But if this subtree had more than one blue edge, then I have effectively actually reduced the number of blue edges also, right? Because now there are no blue edges here, there is just one blue edge incident on the root of this thing. So the size of R prime is at still L, right? I did not exceed my size, correct? Because this one this is at least size 1, so this is L minus 1, at most L minus 1, and I am adding at most 1 edge. So this is still L, this is still an SBA because I did not mess with my root, everything's remained the same. So this is the valid operation. This is what we call a subtree cleanup, okay? So what happens with subtree cleanup is, anytime this property is satisfied that there exists at least one blue edge that is not incident on my V star vertex, I perform this operation again and again. Doing it as many times as needed will give me a SBA in which the blue edges are all incident on V star. So can you tell me what this means in sort of realistic term, as in terms of the tournament fixing problem featuring players and so on? What does this mean? See, at the beginning we started out by saying that in the seeding is a very sort of how you fix the seeding is a rather complex question, like what seeding would favor V star, because in that original example at the very beginning when we saw briefly, like it does, who you play in each round, okay, is determined by who plays whom in the other matches, right? Because when you move from round I to I plus 1, okay, who all won round I will determine who you will play in I plus 1, right? So it is not absurd to think that in order to rig the tournament in favor of my favorite player, it might need me to actually fix games that involve other players. Because if I knew there were certain opponents that are particularly easy for me to beat, for my team to beat, then I can just ensure that only those people win, and therefore I will always have an easy path to this thing. That is what this SBA was doing. But what we are saying is, by the valid subtree clean operation, we note that if there exists a solution of this kind, then there also exists a solution that requires me to only fix matches involving my favorite team. Okay? That is the outcome. So then what this does is sort of narrows the number of possibilities I need to check. As long as I know who will play against my favorite team, okay, my favorite team, and then I know who I have to fix and so on. So sort of this seems to give more structure on what all matches to fix. Okay. The next property is what we call the cyclic shift property. Now, in this case, so here the topological ordering is the natural, so V1 first, followed by V2, V3, okay, so like this, V4 and so on. So this is an incomplete tree, just the portion that is relevant to us has been described. So obviously this has what, 23 it will have, you basically will complete this in sort of make it an SBA. So this is the part where the sort of thing that is relevant to us is happening. So in this case, what this topological order means is that V2 in the topological order, V1 appears before V2. Okay, V1 is nowhere to be found here in this example. So before V6, okay, so let me just write this here. So V1 doesn't actually appear. So V2 is the first thing. V5, V3 also does not appear. Okay, V4. Okay, V2, V4. V5, V6, V7, V8, V9, V11 and V23. Okay, so just sort of this is the topological ordering that we are looking at. Okay, so the blue edges are the ones that are the reversed edges. Okay, so why are they reversed edges? See, in terms of this topological ordering, V4 should beat V6, right, because this is how it goes. So here these are all unaffected vertices, assuming that these are all the sort of a non-upset vertices. Okay, so all arcs are going from left to right. So V4 should be beating V6, but here we see that actually that match has been rigged, that match has been fixed, and then again V11 and V5, clearly V5 beats V11, but that game has also been fixed. Okay, so this is the situation. So here now, okay, so the example here is this thing. Okay, so let me just, okay, so I perform this operation. It is performed when I have a path, subpath, okay, from P1. Okay, so I should give a definition first actually. Okay, sorry, I should have introduced a definition before. So let's just okay, let's just see here first. Okay, all right. So suppose this is the example that we had for the graph D. Okay, I'll just introduce a small definition and then we'll come back and complete that operation. I'm sorry, I just forgot that I should have said that before. So this is the graph that we were looking at. This is suppose the topological ordering. Okay, so these are the black edges are the normal regular edges, the red edges are these upset matchups. So in this case, we will define this thing called type. Okay, so we identify where all these affected vertices sit. These are the ones. Okay, now I look at the whole ordering and break it into these chunks. So look at the first affected vertex that appears in the topological order. Okay, that has type 2. If there are any unaffected vertices that appear before it, they are called type 1. If this set is empty, meaning the first vertex that appears in my set is an affected vertex, then this does not exist, and that vertex itself is a type 1 vertex. Okay, so this is the way I sort of split this thing. So the next so it's possible that between C and D there were other vertices which were unaffected vertices. They would have type 3, and then again when I see so basically the whole topological order is broken into these chunks. These are the unaffected vertices, these are the affected vertices, these are the unaffected, so this way. Okay, so because we have k affected vertices, correct, we assume that k is the number of sort of affected set. Notice that there can be k plus 1 types. Do you see why? Because between these affected vertices there are k minus 1 gaps. There is one gap at the front, and then of course there is one gap at suppose this is the last thing. So they are basically, they can have k plus 1 types. Okay, this is what I mean by a type. Okay, so now let's just go back to this thing previous. Okay, so I apply this cyclic shift operation if I have this particular path in my SBA. So this is B, again I have R, the blue edges, and this is here LS2. Okay, so this is P1 to PQ. This is a path that exists in this tree, okay, in this SBA. They all have same type. Okay, let's call it type I. Is it fine? So basically if I look at that this topological order, it means that if I is greater than 1, okay, so it means that strictly greater than 1, that this is the block within which these vertices appear. These vertices are all from outside of, they are unaffected vertices. Okay, so they are from the set, this means that they are not the affected vertices, and they all sit in one of these blocks. So this is the I minus 1th type, this is the affected vertex which has type I minus 1, and it's followed by another affected vertex which is of type I. Okay, so P1 to PQ is of this kind. All right. Furthermore, see in this set there can be many vertices, right? So all I am saying is from between P, this, if I look at the subtournament induced on only these subset of vertices, that is an acyclic subtournament. Do you agree? There are no cycles here because all the arcs are going left to right. So it is not, so conceivably it's possible that in this large set I pick out some q vertices which sort of appear from left to right, but that not necessarily they are not like consecutive, but we require that here. This is basically that P1, P2, PQ, they appear consecutively, okay. So here also. Is this clear? So this, I need this property as well. So basically they will appear, this P1 to PQ appears in a block. Furthermore, I also need that there exists P0, okay, same type, and it is the player that is immediately preceding P1 in the topological order. So I will write it as preceding P1, okay. Preceding means with respect to the topological ordering. See, P0 is not part of this path P, okay. Any questions so far? So lots of properties, lots of things to check, okay. Now they are of the same type, either the whole block of the same type must have the same relative ordering with x and y, because x and y have a different type. No, so because these are unaffected, the type I vertices, the one that appeared in like a bunch of them, because they are unaffected, at least the ones that we are talking about, yes, because they do not have any back arcs. So if one of them, that's a very important property used in the proof, that if one of them is an in neighbor of x, all of them is an in neighbor of x, and opposite is also true if one of them is an out neighbor. So for types, vertices of the same type, you can say this. And the reason why every affected vertex has a unique type is because this relationship does not hold for them, because you are allowing back arcs and all. The adjacency relationships between two different affected vertex, it cannot be captured that way. When we say that multiple vertices have of the same type, what we are basically saying is they are sort of equivalent vis-a-vis their out neighbors and in neighbors. That's precisely, that's a very good question, okay, that what's actually happening. That's the thing that we are trying to zero in on, okay. So now P0 is this vertex that precedes P1 in this sort of topological order, has the same type, but P0 is not the parent of P1 in this SBA, okay. Lots of properties to see. So let's just see the example what I'm trying to say. So this is V5 is P0, okay. P1 is say V6, V7 could be, yeah, okay, right. So yeah, so these are all these edges sort of going through, okay. Now can you say, do you like by the properties that I listed right now, right, do you think that P will have any blue arcs, meaning are any of these arcs in P reversed? Because P is a path in this graph, in this SBA. So I said nothing about blue arcs per se, like explicitly I didn't say anything. I said P is a path, so it could have blue arcs, right? So the question is, can it have blue arcs or can it not have, like do you see what's sort of going on? See, because I said that P1 to PQ is not only a path in this graph, but P1 to PQ are consecutive vertices in the topological ordering, and they have type what? They have the same type. right? So meaning what? That they are like in between two affected vertices. In between, they are a directed acyclic graph. This path that it appears here also appears in the topological, this ordering, the same ordering holds in the topological order. This topological order is on the original graph, the win-loss graph, which does not have reversed edges. Therefore, P, this path cannot have any reversed edges. So it is a blue free path. Okay, that is kind of important. Okay, so this is the situation. So this is P1, P2, P3. If you look here, that V6, 7, 8, this is the type. Sorry, no, not this one. So in this case, because none of the affected vertices are mentioned, we can assume that all of them are of the same type. Okay, like all of them, like meaning they are all unaffected vertices, so they are like they are not affected vertices, so this thing. So okay, so this is V5, V6, V7. So V5 is the parent P0 which appears before V6, see before P1, but V5 is not the parent of P1 of V6 in this graph, because the parent of V6 is V2. This is the situation in which I can sort of perform cyclic shift. So now can you guess what happens? What I am going to do is say that I am going to move P0. P0 is a parent of V6, which is my current P1, right? My path starts at P1. I will make an adjustment that I will force P0 to be part of this path. And P1, P2 and other things will appear, but obviously if I want to keep the same length, PQ, which is the last vertex, it will no longer be part of the same path of the same length, because P0 is now being inserted. So PQ will basically take on the position of P0. Okay, so if you look here, this is what is happening. V5 becomes the parent. I already know there exists an arc between V5 and V6 in this order, because this is the this is told to me by this property, that P1 is the precedes P0. So from this, I know that from my diagram, from this topological order and the fact that I have the win-loss graph, this edge P0 to P1 exists. So this edge is the one that this is it. So this is that P0 to P1 edge. Okay. So then P1 to P2 edge is this thing. That remains the same. It has just moved one level, right? Now P2 to P3, this is the last edge. Basically PQ minus 1 to PQ. This last edge that appears in this path P, that no longer exists in this SBA, because V8 has taken on the position of V5. So if you see V8 appears in the original position of V5, this is what this is, and V5 has now become the parent of P1. Okay. Now now I ask you, well, if just by making V5 can very well become the parent of V6 and take on the subtree, and then we move V8 from down below, but what happens to the other edges? Why, like what is the relationship between this new P0 which is sitting here and all the other subtrees to like the other children of the original P1? Can you say why, like do you see what the relationship will be? What is the relation, what is happening here between remember these are of the same type, right? So what is the relationship between V6 and V11 and V11 and V5? No? So, okay. So in this example, it is sort of clear to see that if V6 is the pair is an in neighbor of V11, meaning if there is an arc going from V6 to V11, because these are all the vertices of the same type, V5 is even a stronger player than V6. This is this portion of the, if I look at the subtournament here, this is an acyclic subtournament. So, if V6 was beating V11, V5 will also beat V11. So, this edge was not, this edge that we have V5 to V11 was not used in this SBA, but it exists in my original graph D. So, this is, I add this, this is a non-reversed edge, correct? Now, it is possible that there were, now on P1, think about all the, so what is happening is basically that the number of reversed edges incident on any of these vertices in P, okay, say on Pi, the same number of reversed edges is incident now on Pi plus 1.